All right, thank you guys for having me. So today I'm going to be talking about the waffle method, how to make them and how to mill them. Many people may have heard this talk before, but hopefully it's still quite entertaining. Okay, so there's some issues with conventional plunge freezing cells. Everyone knows how this is done. You put your cells onto a grid, or you can grow them on the grid. You put them in a Leica or a Vitrobot. The Vitrobot, you would want to put Teflon on one of the blotters in order to just back blot your sample. Or you could use a Leica that already does just one-sided, single-sided blotting. So vitrification is not guaranteed for the thicker samples, like anything more than 10 microns. You could try to add some glycerol in there and it may work, but it's not guaranteed. Other issues with that is that you have preferred orientation of your cells all laying the same exact way on your grids, and then you'll have a very small usable area. This is okay if you're doing thin edge tomography, so you'll just look at the very thin edge of the cell that you could actually see in a TEM. But if you're looking in the main bulk of the cell, usually that's too large and it requires FIB-milling. So if you're going to do that and you only have these single cells on the grid, your lamella are going to be extremely small and your throughput is going to be pretty low. And because of the preferred orientation, you're going to get basically the same visible area in your lamella per cell that you mill. So one of the ways to combat this is the waffle method. So it just is basically you put your cells, a very high concentration of your cells, onto a grid, sandwich them into planchettes, and then you high pressure freeze them. And we applied the sample to the grid bar side, so it should fill in all of the square. And your sample thickness will be dictated by the thickness of the grid bars, which is around 20-25 microns. And this solves the issues of preferred orientation because your sample will be randomly orientated within the 20-25 microns of that bulk. And every part of the lamella will be usable and you'll get multiple cells per lamella most of the time. So here it's the image on the right is just mycobacteria, and this was plunge frozen. So you just see the one and how kind of small it is. It's pretty narrow but long, but your lamella will be very, very small if you try to mill through this. And with the waffle method, you could see that there's a ton of cells here. And this is just one of the images that we got from one of the lamella that we have made over time. Okay, so just to show the differences between a plunge frozen grid and a waffle grid, this is just yeast. So on the left, you could see there's just like random clumps of yeast. It's kind of, you can't predict where it's going to be in the square. Ideally, it'll be in the middle of the square so that you can mill, but anything close to grid bars, if it's not the proper orientation, you won't be able to mill it. And on the right, you can see that the yeast are everywhere. And basically we can mill anywhere within that square and get a really good lamella. So this is just the same thing, but in a FIB. So you could see the clumps on the left and then how they're filled in on the right. I know there's a lot of questions on, can you see grid bars? Yes, like clearly you can see the grid bars here. If your sample happens to be thicker because you use a spacer, which will allow for more sample. If your sample is larger, let's say like a Drosophila eggs or something like that, that you want to freeze and not completely just squish them down. You could use a spacer and then you won't be able to see the grid bars that well, but you could just increase the voltage from 2 to like 30, and you should just take a really quick image and you should be able to see the grid bars. Or you could figure it out from the holes. Okay, and this is just, again, another view of the plunge frozen grid and the waffle grid just from an angle. So you could see the clumps of yeast. You could see on the right, you can't tell that the yeast are there, but you know that they're there. You could kind of see some little divoted pockets on the surface, and that basically is because of all the yeast that are packed in there. Okay, so an example that's not yeast. So this is in the original waffle paper. This is microsporidia. So the B and A, you can see that it's just a plunge frozen grid with the microsporidia on there. They all lay in the same, basically the same orientation. The lamella that you're getting are extremely small. It's like 2 microns wide, and it wasn't even usable once we moved it from the FIB to the Krios. Uncollectible, most of them just like break apart. They're very, very small and fragile. And then on the bottom, C and D, we just applied a high concentration, made the waffle, and you can see that they're all there within the lamella in different orientations. And they were specifically looking at these polar tubes within the microsporidia that they shoot out to infect host cells. And they were able to see them in different orientations. So that was very helpful for them. Okay, this is kind of like a gag slide at this point, that you could do the waffle method in 11 easy steps, because it's actually not quite easy for beginners, but if you do it a lot over time, it'll get much easier. So the first thing that we do is polish the planchettes, or the HPF hats. These we got from Ted Pella. They're just brass. I think you could get them also in aluminum, gold-coated copper. So it's whatever you want to use. We prefer these for absolutely no reason. We just had them. So first, they come with these circles all along the flat side. On the opposite side, there's a cavity that's, I think, 3 millimeters, or 0.3 millimeters, sorry. And then, so these are type B planchettes. Type A planchettes have a 0.2 millimeter cavity on one side and a 0.1 cavity on the other side, but we don't use those for this specific method. We like the flat sides. So they come with these circles that are just straight from the manufacturer, and we want to get rid of it because the flatter that surface is, it will dictate what the surface of your waffle will be like, and then your lamella will just be much nicer if you have a flatter surface versus like a very like rocky surface. So on the left here, I have some not polished ones. You could see the scratches on the surface. You could kind of see the circles there. And then we just sand them down on sandpaper. First, it's about 1200 grit. And then we do an intermediate, like maybe 7,000 to 8,000. And then we do about 12,000 to 15,000 for the last grit. So you could see progressively the deep scratches are just sanded away, and the surface becomes pretty smooth, but not smooth enough. So after this, we normally polish with a metal polish. This will just, get rid of any real surface imperfections and provide like this little wax layer on top of the planchettes to help with the hydrophobicity of the planchettes to allow for separation later. And we just polish these pretty lightly on the surface of, I do a filter paper, someone else does an index card. Any surface like this would work. And you just get rid of everything, get rid of some excess with a Kim wipe, and then go back, finally getting everything off. And they'll be very, very shiny at the end. Okay, and the next step will be applying hexadecene. So it's just applied like this. Normally I apply a droplet on top and kind of bring it down with the pipette tip so it gets all around as well, and then apply a final droplet. And I normally leave that on for at least 15 minutes or until I'm going to use them to assemble the waffle later. And this also helps with the separation of the hats once it's sandwiched together and frozen. Okay, we coat our grids with an extra 20 nanometers of carbon. So the grids that we currently use are quantifoil 2.2s, that doesn't matter, but they're 200 mesh. So the squares are about 85 microns large. And that's very helpful for the pre-cuts that I'll show you later. But anything smaller than 200 mesh, your lamella is going to be limited in length. So we find that this is 200 mesh is like a sweet spot. So then we plasma clean the grids, and we're applying the sample to the grid bar side because you want it to sit within the grid bars, fill up that whole section. So that's the side that we plasma clean, and we normally do it for 30 seconds with just hydrogen, oxygen. Then it's time to assemble the waffle. So here I just have some images of the process. So the bottom planchette goes in with the polished side up, and then you would put your glow discharged grid on top with the grid bar sides facing up. Apply your sample. 5 microliters is normally enough. I think you could do about 4, but you really want to like squish in all that sample. There will be some spillage, but that's good because then it's, that it's actually filling the grid squares. And to mention, we normally add like 5% glycerol to our samples now. We found that this helped with the vitrification in between the cells. So any of the buffer, sometimes it was like a maybe 50-50 perhaps a chance that it would be non-vitreous ice in between the cells and the cells would be perfectly vitreous. So the glycerol just helps ensure that everything will be vitreous on your lamella. Then you apply the top planchet with the flat side or polished side facing down, and it kind of just makes a little sandwich. Then you close the tip, you lock it, and this is for specifically a Woolwind. I think we have a compact 01. And then you HPF, and it makes a very loud bang. So after this, you would say, separate the hats, take the grid, and then you would go clip it. So we clip them in a notched auto grid. This is very specific for a FIB-sem. And it comes with a notch, 2 dots, and then a double dot on the other side of the notch. So normally I would Sharpie this in just so I'm able to see the notch better. But specifically for clipping, I like to orient the grid bars to the notch so that they're parallel. And this requires me marking it with a Sharpie along the notch and just kind of dragging it along the side and the top so that when I clip, I could see where the notch is based on that Sharpie mark. And I do this under a stereoscope, just use tweezers, rotate the grid until, it's about parallel, and then clip it down. So that's just an example. I would say the notch is probably on the bottom here. It was in my photo. Okay. And just to mention 2 things that helped us increase our throughput. Before we were only able to do really 2 to 3 waffle lamella per day. Within an 8-hour workday. So I would set it up, let them run, and then save them at the end of the day because of the amorphous ice contamination that was accumulating on the lamella if we went overnight. So we got the Delmic ice shield that greatly helped with this. I think our initial reading was about 5 to 6 nanometers per hour of amorphous ice contamination, and now it's about 1.5. And this was measured, I think, like a year ago when we installed it. So I probably should do another measurement and see what it's like now. But I am able to do 12 to 16 lamella based on time overnight. And also we got this angstrom doer. I know MCCET got one. So it's attached to their Aquilose. It holds, I think, 175 liters versus the 35 liter that comes with the Aquilose. So normally I just fill it in the morning on Monday, and it lasts until about like Friday morning. I would get very nervous if I don't refill it if I'm doing another mill overnight from Friday to Saturday. Okay. So after you clip and you put it in the Aquilose, I just use maps to take a tile set of the entire grid. So on the left is the grid there. You could clearly see the grid bars. You see all the squares. It's pretty much aligned to the notch very decently. And on the right is just after we do all the pre-cuts. So those were the sites that I decided to mill just based on the surface of each of those squares. So I'll go to the ones that are basically the flattest and do my my milling there. I also use maps for fluorescent overlay. So again, just the waffle grid on the left. In the middle was a fluorescent image from our Zeiss AriScan that someone had used. We also have an IFLM, but we don't really use it. The resolution is kind of low, and we can't get an overall view of our grid. We could only see 4 squares at a time, so it's not very useful for us when we want to do some type of targeted milling. So we prefer to do Zeiss AriScan first, put the grids in the Aquilose. The ice contamination is super minimal. This was a grid for someone who barely handles grids ever, and there's barely any ice contamination on the surface besides what you would get just from the HPF. So the person was able to label all the cells that they would like to mill, and then in maps, you can just upload the image and do a 3-point correlation, and you can adjust your fluorescent map to overlay completely on top of your tile set in maps. So that's very helpful for targeted milling. An issue with this is that you can't really tell where things are in Z, so you kind of just place your pre-cuts and where your lamella will be in hopes of getting the cell in your lamella, but it's also kind of hard, so the more cells you have, the better. Okay, so there's a lot of manual preparation steps that happen for waffle milling versus just single cell milling. We have to do a pre-cut, pre-clean, notches, and then the final lamella placement. For 16 lamella, it takes me about 5 to 6 hours, depending on how fast everything's milling and how like thin the sample happens to be, or how thin the bulk happens to be. So first, going over pre-cuts, placing the pre-cuts. So in maps, I arbitrarily just select some squares that I think look good. And then I actually go to them by rotating the grid into and tilting into an orthogonal position. So the grid is orthogonal to the ion beam. So you're just milling at 90 degrees. And you can see here, there's some weird surface texture on the square, but it doesn't really matter because I'm able to just kind of move it over to where the flat surface is. And this is exactly why I like to orient the grid so that the grid bars are parallel to the notch. Because if they were, let's say, diagonal, you could do a larger lamella and place your precuts further apart. But you can't really have any wiggle room moving it to the left or the right because the grid bars will come in. And you want to avoid the grid bars. The larger that top pre-cut is, which will be the bottom pre-cut later on after we rotate it back, the better, because you can see the bottom of the bulk when we do our pre-cleans. And the smaller pre-cut there is just so that when you put it in, when you have your final lamella and you put it in a Krios and you're doing a tilt series, you don't run into bulk. So I like to also place a mill pattern right below where I would like to potentially place my pre-cuts so that I could figure out where the grid bar is so the grid bar doesn't cut into my pre-cut again. Because if it does, if it's like right at the surface of the pre-cut and then I have my, it's grid bar and then the lamella area and then the other pre-cut, it's basically completely unusable. Or you could mill out a very tiny section, but then your lamella is going to be extremely, extremely small, and that's kind of pointless at that point. I would just do another one. Okay, so for pre-cleans, it's kind of hard to see here. These are screen grabs from our Waffle protocol that shows like a very in-depth multiple videos of how to prepare everything for the HPF and then also how to mill these. So just starting with the left column, the top one is just at 41 degrees. You can tilt this higher or lower depending on how thick your sample is. If you could see that bottom here, I could kind of see that there's a horizontal line there. But if you're not sure, you could place your mill box just to cover the whole entire pre-cut so that you can see the bottom. And the left bottom image is of it actively patterning, and then you can see all that bulk that's underneath. And then we just move in about 10-degree increments. So the next one is 30 and the next one is 20. Just cleaning out all that bulk underneath. If you have any bulk underneath and you go and put it in a Krios after you mill your lamella, you will see that you can't see your lamella because there's a ton of stuff underneath your lamella, and then your whole session was basically pointless. Which is very unfortunate. So after we do all the pre-cleans, we add in this notch for stress relief. You're able to kind of, well, the pre-cuts are about 20 microns wide. You can make them as wide as you want. Our lamella normally are 12 microns wide, so we have some wiggle room as to where to place this notch. Let's say there was a crack in the surface, I would just move the notch to the other side. You can move it in a bit to avoid any like ice contamination on the surface. And this is very important for it to be milled all the way through, or else you'll get some buckling in your lamella because of the stress. So after that, we normally just do autotem. Cryo, I have 2.4. I'm not sure if there's a new version yet. I know there's a new version of maps, but I haven't had it installed yet. But all the preparation is done here. First, I do eccentricities, and then I'll go to each site and do the pre-cleans and the notches. And then I'll go back into AutoTem, define my milling angle as 20 degrees or whatever milling angle you want, as long as that's your final pre-clean angle and your notch angle. It's very important that you mill the notch at the angle that you're going to mill your lamella at. And then I do the milling angle, the image acquisition, it automatically takes an image. And then the final lamella placement, I like to overlay my rough mill boxes, which is in blue, over my my notch a little bit. I think this helps to ensure that there's complete separation. And I also will place my lamella right in the middle of the notch, about a micron away. And that normally works really well. And then everything else is completely automated once I finish all these steps. So we do all the mill steps in the milling, which is rough, medium, fine, finer, and just decrease the milling currents and the time that it takes to mill. And then in the final polishing steps, we just use like 30 picoamps and then 10 picoamps for polishing. And this is just a video of it actually milling one of the lamella overnight. This is obviously much faster. It normally takes maybe like an hour, 15 minutes per lamella, which is why I'm only really able to do like maximum 16 overnight. And again, this is an example of a final lamella. So you have the overview E-beam view and then the I-beam view on the right. So you could see like it's super thin. You have the notch there. It's definitely completely detached on that one side because it's not buckling and it's very, very straight. And this is pretty typical, like all 16 most likely will look like this unless something's happening with the aquilus and Autotem decides to do whatever it does. Okay, so some issues that can occur with improper setup. Some of these things I don't really see as issues. I don't personally think that an overmill is an issue. I rather make sure that all my material is completely gone before moving on to the next milling steps. And it's done overnight, so I don't really mind. But if you're sitting there doing manual milling, you could just make sure that once it's done milling, you just stop it and move on to the next milling step, because then you're just wasting time. But I don't think it wastes that much time overnight, so I like that. If you have no pre-clean, you could see that there's a bunch of bulk material underneath the lamella, so this will be completely not usable for any tilt series or data collection or anything like that. There's the buckling that I mentioned from an incomplete notch. So if your notch isn't milled all the way through, you don't have that stress relief that it needs. So then it will buckle because of that stress relief versus being able to just like move up and down within that notch placement. And double lamella can occur unless you're doing it manually and you make a mistake. I haven't had any real issues in Autotem giving me double lamella. So it is an issue because then your lamella will be, there's two of them, so it's very thick and most likely, and it won't be usable for data collection. So that is an issue, but I haven't had it happen to me in Autotem before. Okay, so what can we waffle? So I just have some reconstructions of a couple things here. So we have chromosome assembly during yeast replication. We have a plant cell wall synthesis, and we have just single particle ribosomes that we were able to HPF and then mill. And I think this video is pretty cool. So it's a cross-section of a flagella from a trypanosome, and Reza, who's a postdoc here, was able to use TomoSegment TV to be able to segment this. So it's like an auto segmentation program. And then I'm not sure if he put this back in a mirror and selected things. I'm pretty sure he didn't. So this is just straight from that program. And it's able to bring out microtubules and membranes. So I thought that was pretty cool. Okay, and that's my final thing. I have a bunch of QR codes, the Waffle protocol, super in-depth protocol. There's videos, there's explanations. I think it's pretty useful. I'm the one who milled it and did the HPF, so it's exactly like how I would do it. And this was done only early last year, so I don't think I've changed things much. So this will for sure work if you do try it. Our original Waffle paper, our In-Situ website, and then the CryoET portal. If you are interested in doing this method and you have a project, you can apply and specifically ask for us if you want to do Waffle, but I'm pretty sure all the centers are able to do it at this point. And then you could come here and I can teach you how to do it. Yeah, all right, thank you guys.
Thank you, Daija. That was fantastic. Questions? some of our people. So, oh, sorry. Great talk. Thank you. It seems like with the kind of filing down and polishing the planchettes that might be adding a lot of work for you guys. Have you considered seeing if manufacturers would make them just flat for you with no circles?
We have not. It's not that much work for us, and it won't be that much work for you either. So we do them 4 at a time with just like a little pedestal that we get from our tabletop SEM. It's just like the stage. And once we actually do all of the sanding down, we don't do that anymore. So I reuse all my planchettes. So I just have a bunch of planchettes I have already sanded down. And when I go to HPF, all I start with is the polishing, like the metal polish.
Cool. Thank you.
Yeah.
All right, great talk. Have you experimented with the spacers, or what's kind of the maximum thickness that you've done for Waffle?
Yeah, so we have used spacers before. Someone had Drosophila embryos, I believe. And with the spacer that we have, I think it added on maybe like 25 microns of thickness. So it was about 40-50. So they weren't squished down, they were just perfectly intact, and we were able to mill them. So you are able to do it with this method with the spacer. It just took a little while longer because I had to figure out where the grid bars were. But other than that, all the steps are pretty straightforward. It's the same thing. You maybe just have to tilt a little higher during that initial pre-clean to see the bottom, and then work your way up in steps from there. But I currently use the 27-degree shuttle that came with our IFLM. I know they do 35 now. And the maximum that I can tilt, I think, is like 65 degrees. So it's actually pretty high. Like that accommodates a pretty good thickness.
Hi, Daija. I think we can probably take some questions also from the online group. I passed them along to you, but I'm
Sure.
going to read them aloud here as well.
Okay.
So
I see. Yeah.
The first one is the carbon coating on the back side of the grids when you're preparing these?
Yeah, so you just apply it to the actual carbon film side. Yeah, it's just for rigidity when it goes into the HPF.
And the next one is, when you're using the area scan, is that at room temp? And then if so, how do you ensure that there's not movement of sample between FM and freezing?
Yeah, so we have a cryo-linkum stage, so we're able to do everything in cryo. So after we HPF, then we'll put it in the Zeiss. So everything's still completely frozen and cold, so no moving of sample.
I think the last one is more of a kind of trying to get if there's any tricks of the trade. So, this is kind of a question that's come up in other sessions too, is when you're milling and in the absence of an iFlow module, how can you get that right Z height? And do you have any suggestions or tricks that you all use?
Yeah, so that's a really great question. It's very hard to correlate in Z. And because we're milling at 20 degrees and we're getting rid of everything underneath, if it happens to be that the area that you're interested in is underneath, it's going to get milled away. Some things I'm trying to experiment with is milling at a higher angle, but that will make collection slightly more difficult. But I just milled stuff at like 40 degrees, so we're going to test that out to see, so that you're basically able to get like a way better slice through your sample, and maybe you're able to capture that event within the lamella that you're looking for. But yeah, that's if we could do some 3D correlation between the Waffle grids and the fluorescence, it would be insane. That a big game changer. But normally I just try to place my pre-cuts so that the lamella area, kind of where I'm milling my lamella, will start before the cell. And then hopefully I'll get the cell in the middle or maybe at the end of the lamella. But yeah, that's about it.
Okay, thank you very much, Daija.
Yeah.
There's one more question we had also that came in from the chat, and it was, how much concentration of cell do you use when you're doing the high pressure freezing? And also, have you used any cryoprotectants, or do you need to use any cryoprotectants typically?
Yeah, so 5% glycerol, it seems to be okay for all the samples. It doesn't change any like cell composition when freezing, and it helps for everything on the lamella or that you're freezing to be vitreous. Concentration, it depends. It's basically how high can you go? Like if your cells don't like being spun for a very long time at a high speed, then maybe you won't have like that great of a pellet. And that's okay as well. We can do lower concentration. It's just like your cells will be more sparse, but most likely will capture them. But especially if they have something in there that's fluorescently tagged, then we can check in the Zeiss where your cells are if they are at lower concentration. The image that I use, the cells were actually at a lower concentration. It's really hard to yield those. And we're able to just, under fluorescence, be able to figure out where they are within the squares. But yeah, as high as it can possibly go. Normally we ask for someone to spin it down, get a pellet, take everything out, resuspend it in like a very small amount of buffer and a little bit of glycerol, because we need 5 microliters per sample. So if your pellet's really small, I rather just do add 5 or 10 microliters back in, and only maybe do 2, because I rather do 2 with a slightly higher concentration than 4, and they're all very sparse. And you're getting a lot of information and a lot of cells within those lamella anyway, because they're so large. So
I had two quick questions. I was wondering how long you put the cells in glycerol, and is that what you how long they go in the glycerol? And then the other question was, when we've tried this, we've had sometimes a hard time getting the planchettes apart, even when using the hexadeciane. I'm wondering if that's come up and how you troubleshoot that.
yeah, okay. So first, glycerol, I add to the sample like right before I'm going to freeze. So once the sample is prepared and it's ready, add some glycerol in there and then just use it for however many I'm making. So I never add it before or and then keep it like that for a very long period of time. So it's only exposed for maybe as long as it takes to make the amount of grids that I'm making. For the planchette separation, so for our whirlwind, you saw our tip. So the way that it works, it's like a little anchoring system, and then the whole sandwich is here, and you have to poke it out. So I normally apply like a decent amount of force into the poke out, and that actually helps them separate. So normally I'll always have, well, let's say 99% of the time, I will have at least one planchette separate from the grid, and then you kind of just pick the grid up by the rim from the other planchette. Otherwise, they completely separate. And if they don't, I found that a way to help separate them is how you put your tweezers. So you'll kind of put the bottom tip of the tweezer in the section that your planchettes meet, and then the top part of the tweezer up top, and you kind of just do like a torquing motion up, and that helps the bottom planchette just pop out. And this has worked pretty well. I think I taught someone how to do this recently, and they were able to do it that way as well. So I think that's a decent method, but
Thanks.
Any other questions? Well, let's thank Daija again for joining us remotely. We really appreciate you spending your morning with us.
thank you for having me.